The quantum Zeno effect. They say a washed pot never boils. A cute saying, until you discover it's not just metaphor. In the quantum world, it's real. Because the simple act of observing something, just looking at it, can stop it from changing. Not poetically, literally. Picture a single radioactive atom, unstable and ready to decay. Left alone, it follows its own probability curve, a cosmic coin toss ticking toward its moment of transformation. But now imagine you check on it. Again and again, every fraction of a trillionth of a second, whispering, "Have you decayed yet? What about now?" Each time you observe it, the quantum wave guiding its future collapses. The atom snaps back to a definite state, either decayed or not. And if it hasn't decayed, your measurement resets the clock. It's like the universe takes a breath, and you force it to hold it. Watch it fast enough, relentlessly enough, and the atom becomes frozen in time, locked in place. Its decay suspended, not by force or energy, but simply because you're paying attention. Think of it like spamming the pause button on a video game. The world wants to move. Probability wants to unfold. But your gaze becomes a cage. And this isn't sci-fi speculation. Scientists have done it, literally halting quantum systems in laboratories by observing them at just the right rhythm. This idea now sits at the heart of quantum computing, where qubits must remain stable long enough to perform impossible calculations. By watching them in clever ways, we can shield them from the chaos that destroys their quantum behavior. So the next time you sense someone or something is watching, remember, in the quantum world, observation isn't passive. It's power. And sometimes it can stop time itself. Ready for the next secret? The Mpemba effect. Take 2 glasses. Fill one with cold water, the other with steaming hot water. Slide both into the freezer. Every instinct, every science class, tells you the cold one should freeze first. It's already closer to the goal. Less heat to lose. Shorter distance to travel. And yet, sometimes, the hot water wins. Welcome to the Mpemba effect, one of the strangest, most stubborn mysteries in basic physics. A phenomenon argued about since the days of Aristotle, and still sparking debates in modern labs. The name comes from Erasto Mpemba, a Tanzanian student in the 1960s who noticed something bizarre in his school kitchen. His hot ice cream mix froze faster than the cold batch. His teacher laughed it off. Impossible, he said. But a visiting physicist didn't. Tests were run, and the effect proved real. So what's happening here? Why does hot water sometimes break the rules? The truth is, there isn't one explanation. It's a tangled web of competing theories, each capturing part of the picture. Maybe it's evaporation. Hot water loses more mass as vapor, leaving less liquid behind to freeze. Or maybe it's about dissolved gases. Hot water contains fewer of them, and those gases can subtly shift how freezing begins. Then there's the deeper physics. Heat creates powerful convection currents, constantly churning the water. Warm rises, cool sinks, and the entire volume mixes more efficiently, carrying heat out faster than still, cold water. And here's another twist. Cold water can supercool, dropping below freezing without forming ice at all. Hot water, after boiling or heating, may have fewer impurities or altered nucleation sites, allowing crystals to form more readily right at 0 degrees. In the end, the Mpemba effect isn't one neat answer. It's a perfect storm: mass loss, gas content, convection, thermal history, all colliding to produce a result that defies our everyday intuition. A simple question, which freezes first, turns into a doorway to some of the most counterintuitive physics we know. And it raises an even bigger mystery. If something as ordinary as water can betray our expectations, what else in our world isn't behaving the way we think? The nocebo effect. If the placebo effect is the mind's secret superpower, then the nocebo effect is its shadow. Its darker, far more unsettling twin. You already know the placebo story. Take a sugar pill, believe it's real medicine, and somehow your body listens. Pain fades. Symptoms ease. Hope becomes chemistry. But the nocebo effect flips that script. Here, negative expectations take the wheel. Imagine a doctor warning you. This injection might cause a rash. The shot is harmless. Yet hours later, there it is, itching, red, undeniable. Not imagined. Not faked. Your mind creates a physical reaction simply because it expected one. And the evidence for this is everywhere, quiet, persistent, and unsettling. Clinical trials show that when volunteers are warned about possible side effects, the placebo group, those receiving nothing, report those symptoms at shocking rates. Not just, I think I feel something, but genuine, measurable nausea, headaches, dizziness, and pain, all manufactured by their own belief. It mirrors ancient stories of curses, people convinced they're doomed who begin wasting away. Strip away the ritual, the fearsome masks, the chants. And what's left is the pure psychological engine behind it. The nocebo effect at full power. But how does this dark magic actually work? It starts with anxiety. Fear primes the body, flooding it with stress hormones like cortisol and catecholamines. These chemicals warp pain pathways, disrupt digestion, tighten muscles, and send the heart racing. Your brain isn't waiting for something bad to happen. It begins building the outcome in advance. A self-fulfilling prophecy coded into your nervous system. And that has massive consequences for medicine. A doctor's tone, their choice of words, even the expression on their face can shape a patient's physical reality. Say this might hurt, and the pain actually spikes. Say this could cause side effects, and suddenly the body cooperates with that prediction. The nocebo effect is a reminder, a chilling one, that our minds aren't just passengers inside our bodies. They're architects, powerful, creative, and sometimes dangerously so. If belief can heal, what else is it quietly rewriting beneath the surface? The Alice effect. Picture yourself standing beneath a total solar eclipse. The daylight collapses. The temperature drops. Even the animals fall silent, as if the world is holding its breath. But while everyone else is staring at the sky, the real mystery might be unfolding beneath your feet. In 1954, French economist and part-time physicist Maurice Allais was running a routine experiment with a Foucault pendulum, a device that quietly tracks the Earth's rotation by swinging in a constant plane. During an eclipse, something impossible happened. The pendulum's path began to drift, violently, unpredictably, in a way no known physics could explain. For a moment, it was as if the Earth's rotation had glitched. This strange anomaly became known as the Allais effect, the claim that pendulums, gravimeters, and other ultra-sensitive instruments behave bizarrely during solar eclipses. Not always, not predictably, but often enough to unsettle anyone who studies them. The effect is controversial, hard to reproduce, and still considered unsolved. Allais eventually won a Nobel Prize, not in physics, but in economics, adding yet another layer of oddity to the story. Despite that, he stood by his observations for decades. Mainstream scientists have long argued that it's a measurement error. Tiny temperature shifts, localized pressure changes, or the ground flexing as the moon's shadow races across the planet. Those explanations are reasonable, yet they fall short. Some of the recorded deviations are too large, too abrupt, too clean to be brushed aside as environmental noise. And that opens the door to far stranger ideas. Could the alignment of the sun, moon, and Earth create a subtle gravitational anomaly we don't yet understand? Is something like gravitational lensing, not of light, but of gravity itself, briefly altering the pendulum's frame of reference? Does the effect hint at a loophole in general relativity, or even a hidden fifth force of nature? Some theorists have even wondered if the eclipse temporarily interacts with dark matter or some forgotten echo of the old ether theories. Skepticism remains strong, and rightly so. The data is messy. Some eclipses show dramatic anomalies. Others produce nothing at all. Yet the mystery refuses to die. The Allais effect lingers like a whisper in the machinery of the cosmos. A reminder that even within the precise clockwork of celestial mechanics, something strange may stir when the sun goes dark. So what else might the universe be hiding behind those rare moments of shadow? The Benjamin Franklin effect. If you want someone to like you, here's the counterintuitive trick. Don't do them a favor. ask them to do one for you. This strange bit of psychological judo is known as the Benjamin Franklin effect, and it exploits a flaw deep in the wiring of the human mind. The legend goes like this. Franklin had an enemy in the Pennsylvania legislature, a man who openly disliked him. Instead of trying to charm him, Franklin made a curious move. He asked the man to lend him a rare and prized book from his personal library. The rival, taken off guard but slightly flattered, agreed. A week later, Franklin returned the book with a polite note of thanks. And something shifted. The hostility faded. The tension dissolved. The two men eventually became allies, and even friends. Why would a simple favor do that? Because the human brain desperately craves a consistent story about itself. When you help someone, your mind wants that action to make sense. I am a person who helps John is a behavior, but I dislike John is a belief. Those two thoughts collide, grinding together in uncomfortable cognitive dissonance. And the brain hates that feeling, so it looks for an escape hatch. Option 1. I help someone I can't stand for no reason. That feels irrational. Option 2. The easier path. Maybe I don't dislike him after all. Maybe he's not so bad. Maybe I helped him because he deserves it. And just like that, the belief bends to fit the action. The person decides they like you because they helped you, not the other way around. Psychologists have tested this again and again. The results are clear. The more effort someone invests in helping you, the more their brain rewrites the story to favor you. In negotiations, relationships, and sales, this becomes a powerful tool. Ask for a small favor, and you're not just getting assistance. You're prompting the other person to construct a version of reality where you matter. It's subtle. It's clever. And yes, just a little bit devious. So if you ever need someone on your side, sometimes the best strategy is simply to let them open the door themselves. The Baader-Meinhof phenomenon. You learn a strange new word, and suddenly it's everywhere. You spot a car you've never noticed before, and now the streets are full of them. It feels like the universe is winking at you. Maybe a omen, maybe a glitch, but it's none of those things. You're just experiencing the Baader-Meinhof phenomenon, also called frequency illusion, a mental trick so convincing it feels supernatural. It works in 2 stages. First, selective attention. Your brain is the nightclub bouncer of your reality. Every second, it shuts out most of the world, thousands of sights, sounds, and details you never consciously register. But when something new crosses your path, an unfamiliar phrase, a medical term, a car you're thinking of buying, your brain perks up. This matters, it says. Let this one in. From that moment, your perceptual filter changes. The world hasn't shifted, your attention has. That thing was always around you. Now it's on your internal watch list. Then comes stage 2, confirmation bias. Once your attention is primed, every time you notice that word or car again, your brain reacts like it solved a mystery. See? There it is again. I knew this was everywhere. Each new sighting becomes evidence. Evidence that the world is suddenly filled with this one thing. Evidence that you're picking up on some hidden pattern. But you're not discovering a cosmic signal. You're watching your brain reinforce its own expectations. It's a feedback loop. Attention, noticing, validation, stronger attention. Before long, you feel like reality itself has tilted. But what's really changed is the filter between your eyes and your mind. The Baader-Meinhof phenomenon is a reminder of just how curated your reality truly is. You don't see the world as it is. You see the world as your brain decides it should be, which raises a deeper question. If your mind can rewrite reality this easily, what else might it be hiding from you? The Dunning-Kruger effect. In 1995, a man named MacArthur Wheeler walked into 2 banks in broad daylight. With no mask, no disguise, and no attempt to hide his identity. When police later showed him the security footage, he stared in disbelief. "But I wore the juice," he whispered. Wheeler had coated his face in lemon juice, convinced it would make him invisible to cameras. A catastrophic misunderstanding of how invisible ink works. That bizarre moment sparked the curiosity of psychologists David Dunning and Justin Kruger, who uncovered one of the most humbling cognitive traps of the human mind. The Dunning-Kruger effect. At its core, it's simple and brutal. the less someone knows about a subject, the less capable they are of recognizing just how little they know. It's ignorance doubled. A blind spot wrapped inside another blind spot. A terrible chess player doesn't just lose matches. They often lack the strategic understanding to grasp why they lost. They blame luck. They blame distractions. They may even suspect cheating, because they cannot see the vast continent of knowledge that lies beyond their tiny island of understanding. And from that tiny island, the whole world looks small. But the effect works in reverse too. True experts, people who have spent years mastering a skill, tend to underestimate themselves. They're intimately aware of the complexity of their field. They know the mistakes they could make. They assume that what comes easily to them must come easily to everyone else. So the world ends up flipped upside down. The least capable carry the loudest confidence, while the most capable often carry quiet doubt. Suddenly, so much makes sense. The armchair general who believes they can solve geopolitics during lunch. The random commenter who thinks one simple idea can fix climate change. The people who shout the loudest, despite understanding the least. They're not just uninformed. They're unaware of their own ignorance. And that's the real danger. Because wisdom doesn't begin with knowledge. It begins with humility. The ability to look at the world and say, I might be wrong. I might have more to learn. That single sentence is the first step out of the Dunning-Kruger trap, and the first step toward true understanding. The Hawthorne effect. Imagine you want to boost workplace productivity. So you set up cameras, invite researchers with clipboards, announce a brand new efficiency study. Almost overnight, output surges. People move faster. They focus harder. It looks like you've unlocked a breakthrough in management. But then the study ends. The observers leave, and productivity quietly slips back to normal. You didn't discover a miracle. You discovered the Hawthorne effect. Our tendency to change our behavior simply because we know someone is watching. The name comes from a famous series of experiments at the Hawthorne Works factory in Illinois during the 1920s and 1930s. Researchers tried everything: brighter lights, dimmer lights, shorter breaks, longer breaks, even tweaks to pay structures. And strangely, almost every change, good or bad, led to a rise in productivity. Not because the lighting or the schedule worked magic, but because the workers knew they were part of a study. They felt noticed, important, included in something bigger than the daily grind. That awareness created a temporary boost, a kind of social energy where everyone works a little harder because someone is paying attention. For researchers, this is a nightmare. How do you measure genuine behavior when the act of measuring changes the behavior? It's the social version of the uncertainty principle. Observation distorts reality, and the effect reveals something deeply human. We aren't machines reacting to simple inputs like pay, lighting, or break times. We're social creatures wired for recognition. When someone's watching, you're not just doing a job. You're performing. You adjust your posture. You speak differently. You polish a version of yourself for the audience you believe is there. This is why reality TV is never truly real, why employees act differently around their boss, and why we all shape-shift depending on who's paying attention. Because whether we admit it or not, we're always on a stage. And that brings us to the next question. What happens when the audience changes or disappears entirely? The Libet experiment. Think about something simple. Lifting a finger, flexing a wrist, a tiny action that feels like you are deciding it in real time. But what if you aren't? That unsettling question sits at the center of the Libet experiment, one of the most controversial neuroscience studies of the 1980s, a study that cracked open the very idea of free will. Benjamin Libet wired volunteers to an EEG to track brain activity and used an EMG to capture the exact moment their muscles moved. The task was absurdly simple. Move your wrist whenever you feel the urge. And while doing it, watch a special clock and note the exact moment you become aware of the intention to act. Then came the shock. Before participants felt the urge, before the conscious thought "I'm going to move now" even appeared, their brains had already started preparing the movement. A slow rise in neural activity, called the readiness potential, began nearly half a second before the person believed they had chosen to act. Half a second. Your brain fires the first shot, and your conscious mind claims responsibility after the fact. It's like discovering you're not the puppeteer. You're the puppet, politely informed of decisions already made behind the curtain. The implications are dizzying. If unconscious processes initiate our actions before we decide, then is free will a genuine force? Or just a story the brain tells to make sense of behavior it has already launched? Not everyone buys this interpretation. Critics argue that the readiness potential might not represent a decision at all, just a background hum of neural noise rising and falling until one moment crosses a threshold. Others point out how unreliable it is to report the exact moment an intention forms in your mind. But despite the criticism, later studies push the idea even further. Some fMRI experiments can now predict whether you'll press a button with your left or right hand up to 10 seconds before you consciously choose. 10 seconds. That's not free will. That's a spoiler alert. Libet himself tried to soften the blow. Maybe we don't have free will, but we might have free won't. The ability to veto an action at the last moment, canceling the unconscious impulse before it becomes real. But even that offers only a faint pulse. So we're left with a haunting question as we move forward. If our choices begin before we're aware of them, how much of us is actually in control? The uncanny valley. Picture a robot made of metal and plastic, its boxy head and visible joints somehow charming, maybe even cute. Now imagine a robot designed to be perfectly human, synthetic skin, blinking eyes, realistic hair, but something feels off. The smile doesn't reach the eyes. The movements are just slightly too smooth or slightly too jerky. It looks almost human, but not quite. And the feeling it sparks isn't delight. It's a deep, instinctual unease. You've just stepped into the uncanny valley. Coined by roboticist Masahiro Mori, the uncanny valley describes a strange pattern in our emotional response to human-like objects. As an entity becomes more human in appearance, we naturally respond more positively until it's almost human. At that critical point, our feelings drop sharply into discomfort, even revulsion. Only when the human likeness becomes indistinguishable from a real person do our positive reactions return. This explains why nearly realistic CGI characters creep us out more than cartoon characters, and why mannequins in dim rooms can feel terrifying while teddy bears remain endearing. Why does this happen? Evolution provides a clue. Our brains are finely tuned to recognize humans, and more importantly, to spot when something is wrong. An entity that looks human but behaves incorrectly could signal disease, genetic abnormality, or even death. That gut-level revulsion is a survival mechanism, a primal alarm screaming, "Stay away. Something's not right here." Other explanations point to cognitive dissonance, the mental clash between knowing something is not human and perceiving it as human, or a violation of our expectations for how humans should look and move. Whatever the cause, the uncanny valley remains a major hurdle in robotics and animation, a psychological moat separating the human from the almost human. It's proof that our brains come equipped with a creepiness detector that's difficult, if not impossible, to bypass. If you found that as fascinating as I did, hit like, subscribe, and follow Strange Wise for more mind-bending mysteries lurking just beneath reality.